In this video, we're going to talk about partial pressures of gases and effusion and diffusion, and we're going to talk about real versus ideal gases in the next video. So, if you look on pages 194 and 195 of your note packet, it talks about mixtures of gases and how we can evaluate or use the partial pressure of gases. And John Dalton discovered that each gas in a mixture behaves independently. So each gas in a mixture has its molecules moving around. If we had oxygen molecules, they'd all be in a container, they'd all be moving around. And if we have hydrogen molecules in that same container, they'd be moving around. And each would contribute to the pressure independently, so that the total pressure in this container is caused by the hydrogen pressure and the, what else did I say this was, oxygen pressure, added together. So each one is part of the pressure. So the total pressure is equal to the pressure of the oxygen plus the pressure of the hydrogen. And you can see in your notebook or your packet that the total pressure is equal to the partial pressures of each gas in a mixture. And we worked with this last year. Many times we use this when we collect gases over water. So lots of times if let's say we were doing an experiment and we were bubbling in a gas from an experiment over here and the gas went this way. In here it would be all filled with water to begin with, and as the gas came in, it would replace some of the water. And you collect it over water because there's only water in there to begin with, which means there's no other gases that can mix into it. And so when you go to figure out the total pressure, since there's some water in here, some of these water molecules are escaping and creating a vapor pressure. Why can't I write here? So you have to subtract the pressure created from the water from the pressure of your gas, if you want to just know the pressure of your gas. That's called collecting gas over water. And the pressure of your gas that in your experiment would be equal to the total pressure in that case minus the pressure of the water, because you don't want to count the contribution of these water molecules. So that's often how we use partial pressures. We're going to go a little bit deeper, so I'm going to make this picture smaller and bring back this. And you have this in your notes. And in your notes, at the top of this page that you're looking at, we can read, each gas in a mixture of gases behaves independently, which is what I just said. So now let's think a little bit more about my sloppy picture here. I should draw it a little bit better. So I'm drawing a new box of gases. We're going to have black molecules in here. These are supposed to be circles. My pen just isn't working really good right now. So we have our black gas, that's going to be hydrogen, and we're going to have our blue gas, and that'll be oxygen. You know what? I should have drawn this slightly. So we can look at it like this. This is a mixture of hydrogen and oxygen. Now, hydrogen is creating part of the pressure, and oxygen is creating part of the pressure. And so each one occupies part of this container. And I could, not in fact, but in theory, I could pretend that all the hydrogens were here, and all the oxygens were here. So the oxygen gas is occupying a percent of the container. And as we know, percent is part divided by the whole. And the percent, the pressure created by the oxygen gas would equal the percent that it occupies times the whole pressure. So we could find the percent that it occupies if we knew the moles of oxygen that we had and all of them, the total moles of gas in this container. That is called the mole fraction. So if we know the moles, we'll use oxygen as an example, the number of moles of oxygen and the total moles of gas, both hydrogen and oxygen, that would give us, part over whole gives us the percent or the ratio that oxygen occupies. So one way to find the pressure created just by the oxygen is to take the ratio, the percent or the ratio of gas that is just oxygen and multiply that by the total pressure. So if we take the total pressure and we multiply it by the part that is just oxygen, so the moles of oxygen over the total moles of gas, that will give us the pressure of the oxygen, because we're multiplying the total pressure by what part is just made up of oxygen out of the whole thing. This scribble here is called the mole fraction. And so here we have a problem. We have a mixture of 9 grams of oxygen, 18 grams of argon, and 25 grams of carbon dioxide. And the total pressure that exerts, that makes, is 2.4 atmospheres. And we're asked to find the partial pressure of oxygen in the mixture. So I draw my picture, and in here I have oxygen, and I have argon. My pen is really falling apart. And I have carbon dioxide. In fact, I think I have to get a new pen. Hold on. Okay, and here it gives us the mass of the oxygen was 9 grams, and actually, so it gives us all these masses of the gases. It gives us the total pressure and asks us to find the pressure of the oxygen. So we can find the pressure of oxygen if we know what part oxygen makes up out of this whole. What percent is the oxygen out of this whole? And the way we have to do that is to find, well, how many moles of oxygen do we have, and then how many total moles do we have? And then that fraction multiplied the total pressure will give us the pressure of the oxygen. And that's what they've done here. They found the moles of oxygen by taking the mass of oxygen and dividing it by the molar mass of oxygen, which is 32 grams. They found, and I will do that here. So if you know that you have 9.0 grams of oxygen, and you multiply it by the molar mass, which is the same thing as, if you multiply it by the molar mass written that way, that's the same thing as dividing by the molar mass, and you'll get 0.281 moles of oxygen. And you can see that they did that for the argon and the carbon dioxide, and they came up with moles of carbon dioxide, moles of argon, and moles of oxygen. Now to find the fraction, the mole fraction, oh wait, we're asked for the partial pressure of the argon, not the partial pressure of the oxygen. Sorry. To find the partial pressure of the argon, we have to find the mole fraction of the argon. And they do that here by taking the moles of argon and dividing it by the total moles of the gases. So the moles of argon is 0.451, but they had to add up all the moles of the gases to get the total moles. And then when they divide 0.451 by 1.30, which is just these three things added up, they get a fraction which in decimal form is 0.347. So now they can take the total pressure, which they gave us, 2.454 atmospheres, multiply it by the fraction that is argon, and that gives you the pressure that is argon. So that's how you can use mole fractions to find the partial pressure of a gas. Okay, now we're going to talk about a fusion and diffusion. And a fusion, you can see on the top of page 197, means the escape of gases through a tiny hole into an evacuated space. That means escape into a vacuum. And you can remember that effusion, escape. Diffusion means the mixing of two gases. So if you have one gas on one side and one gas on another, and there's a divider, and you open the divider, how fast will they mix? That is diffusion. And there is a law that goes along with this, but we're not going to learn it. It's in your book, but it's called Graham's law. But sometimes we're going to think about it just in concept. Sometimes we are concerned about how fast gases will effuse or diffuse, how fast they'll escape, or how fast they will mix. And what's important to realize here, at the same temperature, this is very important, all gases have the same kinetic energy. So why don't they mix at the same rate if they have the same kinetic energy? Because they do not mix at the same rate. And here is where physics comes into play. Kinetic energy is equal to 1/2 the mass times your speed or your velocity squared. So kinetic energy is proportional to mass and to your speed squared. Substances that have a greater mass, molecules that have a greater mass, when this is bigger, then the velocity will be smaller. So these two things written right here, the mass and the velocity, are inversely proportional. So if mass goes up, then the speed or the velocity decreases, because speed and velocity are almost the same. So substances that have molecules that have a bigger mass, and let's look on the graph. Oxygen here has a much greater mass as a molecule than helium or hydrogen. And you can see that the fraction of molecules, most of oxygen's speeds of all their molecules is over here at 5 times 10 to the second. When we're dealing with molecules that are lighter, like helium or hydrogen, most of their molecules, the biggest fraction of molecules have a speed that's 10 times 10 to the second. And for hydrogen molecules, it's even less because the mass is less. So the speed of a molecule will be inversely proportional to its mass. If you have a bigger mass, you will have a slower speed. And so we can use that relationship. Gases that diffuse slower will have a slower speed. They will have a bigger mass. So conceptually, you want to be able to process that.